So now classification of power amplifiers. So power amplifiers are classified into A, B, C, D, E, F. And one basic thing, remember, A is the highest linear power amplifier, and F is the highest non-linear power amplifier. So when linearity is very high, efficiency is less. When linearity is less, efficiency is high. So A will have very least amount of efficiency, F will have the highest amount of efficiency. So please understand this basics. You might be knowing. I'm just recollecting the basics. Class A amplifiers, if the transistor is operating for the entire cycle of the input signal. So 360-degree operation is available in the Class A amplifier. So that is why if you find out the efficiency, if you're for a normal Class A power amplifier with normal resistor RC coupling, capacitor coupling, we will be having the efficiency be 25%. When you are going to use a balloon transformer, you are going to have an efficiency of 50%. So 50% efficiency means 50% amplification, 50% power loss. Okay, so power loss is a serious issue in Class A power amplifiers because it is linear. All linear circuits will have reduced efficiency. Okay, the power loss happens because we have the peak voltage across the drain source VDS. Across the drain and source, we have the peak voltage swing. So relatively, the channel is there and current is going to flow through the channel. Channel is going to be resistive. So power loss is inevitable. So Class A amplifiers are going to have maximum of 50% efficiency theoretically. Practically, it will be even more less than 50%. And transistor is going to be in transistor is not transistor is operating for the entire 360 degrees, right? So when transistor is operating, power loss will be there. You cannot make it zero. And because you have a matching network will also consume some amount of power. So when you consider all these three cases, you can find out the efficiency. You can find out the three cases of efficiency here. The first case is the supply voltage and bias current remain constant. Second case, supply voltage is unchanged, but bias current is reduced. Third case, both are reduced. So three different cases where they are finding out the efficiency. In the first case, they got the efficiency as Vp square by 2 VDD square. Second case, Vp by 2 VDD. And in the third case, they got the efficiency as 50%. It is constant. So see here, eta 3 is 50%, and eta 1 and eta 2, they will try to reach 50% when VPP equal to VD. So this is the most desirable and it is difficult to design PHA with a variable supply voltage. So conventionally in BJT based power amplifiers, we would not have given importance to these three conditions, but here three conditions are possible. I again repeat, one is supply voltage and bias current are constant for whatever power operating power. Second one, supply voltage is constant, but bias current is reduced. Next one, both are reduced. So I am computing three efficiency, eta 1, eta 2, eta 3. Eta 3 is highest among all the three, and eta 1, eta 2 slowly grow and touch the value of eta 3. Conduction angle is very, very important. So conduction angle will say how much degrees the transistor is conducting. For Class A, it is conducting for the entire duration of input cycle. So the conduction angle is going to be 360 degrees for Class A power amplifier because the transistor is turned on always. But for Class B, you see it is on only for one half of the input signal. So the conduction angle is only 180. So in the transistor is conducting only for 180, and for other 180, the transistor is not conducting. I am saving the power. When power is going to be saved, efficiency is going to be increasing. So Class B is efficient more compared to Class A.